Over the past century, scientists have been super interested in the concept of black holes. This interest began to gain momentum around 1916 and has become a major puzzle in astronomy. These strange objects in space are places where gravity behaves in extreme and unusual ways. A black hole, maybe 2 to 4 million times heavier than our Sun, is still a big question mark. Despite numerous research efforts, we've gone from knowing next to nothing to determining some specifics, with new discoveries being made all the time. Yakubu's most recent find includes some surprising information about the contents of black holes that could alter our worldview. It challenges what we thought we knew and provides us with new methods of observing these space objects. These new insights might lead to more investigations into potential things we've missed. Come explore the cool world of black holes with us and see what secrets are concealed within the vast universe. So, what are black holes anyway? Before we get into Yakubu's latest findings, let's go over the fundamentals. Most people have a general notion of what a black hole is, but important details are still unclear. Back in 1916, Albert Einstein's great theory of general relativity suggested that black holes ought to exist. But at the time, it was merely an idea. It took about 50 years to find actual proof that black holes are real phenomena in space. In the 1960s, when scientists were studying a star named X1 that was emitting X-rays, they noticed that the X-rays were moving in a systematic manner and being sucked into something dense and invisible. This thing, which turned out to be a black hole, totally changed how we viewed space. It was a huge deal because it demonstrated that black holes weren't just theoretical, they were real, mysterious, and needed to be studied. Everywhere, scientists began attempting to learn all they could about black holes. They discovered that our galaxy alone might contain around 100 million black holes. But finding them is difficult, so that number is just an estimate. Black holes are incredibly hard to spot. According to scientists, millions of black holes may be concealing themselves within our galaxy, which makes understanding them even more important. Let's discuss how gravity works in black holes. Black holes have so much gravity that anything that gets close is crushed into a tiny point known as a singularity, where physics no longer functions as we know it. In essence, black holes resemble enormous vacuum cleaners in space, sucking everything up. One of the most terrifying aspects of black holes is what would happen if you fell into one. You'd get stretched out and torn apart by the insane gravity before you were destroyed. So it's best to stay far away. Despite the fact that black holes are everywhere, the closest one is about 500 light-years away, which is still a little unsettling. In 2021, scientists did something amazing. They captured the first clear picture of a black hole, the M87 black hole. It took many nights of taking pictures and combining them to make one image. With this new information, researchers discovered that black holes have 3 layers, even though people often believe they are just empty holes. The first layer is called the event horizon, the point at which nothing can escape. If something crosses that line, it's going in. The second layer is the photon sphere, where gravity is so strong that even light cannot escape. Then there's the singularity, where everything gets crushed into a tiny point and the laws of reality break down. Physics ceases to exist there. What's even cooler is that every black hole is different. While they all have those 3 layers, they behave in unique ways. They're hard to study because our usual scientific methods don't work. Scientists have to examine them indirectly, by analyzing the radiation they emit or the gas and dust swirling around them. You can't send a probe into a black hole because anything that crosses the event horizon gets pulled into the singularity and destroyed. So there's no point in wasting billions on probes that won't send back any useful data. That means black holes must be studied by researchers indirectly. And while black holes are really 3-dimensional, scientists often model them in 2 dimensions to better understand them. To make things even trickier, no 2 black holes are the same. When we study them, we must remember that physics as we know it doesn't always apply. Current theories suggest that black holes form when massive stars collapse. A star can no longer fight against its own gravity once it runs out of fuel. If it's large enough, it collapses into a black hole, eventually becoming a singularity. To learn more about black holes, NASA scientists studied the center of the M87 galaxy. They saw a huge swirl of hydrogen gas spinning incredibly fast, about 1.2 million miles per hour. That gas would normally split apart due to centrifugal force, but it stayed together, indicating that something massive was holding it in place, likely a black hole about 3 billion times heavier than our Sun. Another fascinating idea came from Roy Kerr, a mathematician from New Zealand. In 1963, he used Einstein's equations to describe how rotating black holes act. He said that instead of collapsing into a point, a rotating black hole forms a thin ring called the ergosphere. This spinning ring is crucial to understanding how physics breaks down near black holes. Kerr's idea also proposed the possibility of an Einstein-Rosen bridge, which is similar to a wormhole. This could, in theory, allow travel through space-time, connecting distant parts of the universe, or even other universes. To understand wormholes, you need to be familiar with space-time, which, according to Einstein's theory, is a four-dimensional fabric that gets bent by heavy objects. This bending causes gravity, which affects how objects move. Think of space-time like a piece of paper. If you fold it, you create a shortcut between 2 points. That shortcut is a wormhole, a hypothetical way to travel through space and time almost instantly. Wormholes remain theoretical, no proof exists yet that they are real. But they are a byproduct of general relativity. One of the challenges with wormholes is that they are predicted to be unstable. They would likely collapse if formed. The idea of using wormholes to travel across the universe, or even through time, has fascinated physicists for decades. One particular kind of wormhole, called the CR wormhole, has gained attention. Named after Roy Kerr, it's a speculative model that could link two distant points in space, maybe even across different universes or timelines. It would be amazing to use wormholes for time travel or interstellar journeys. However, significant problems remain. Wormholes are thought to be unstable, and the forces and radiation surrounding them would likely make travel through them nearly impossible. Some scientists argue that Einstein's equations are good for understanding gravity but don't explain the quantum forces that control radiation and microscopic particles. To truly comprehend black holes and wormholes, we may need a new theory, one that combines gravity with quantum mechanics. That's what Michio Kaku and other physicists have been working on for years. One promising idea is superstring theory, which suggests that even subatomic particles are made of tiny, vibrating strings. Superstring theory proposes that everything in the universe, from the smallest particle to the largest galaxy, is made up of tiny vibrating strings of energy. These strings exist not just in our familiar 3 dimensions, but in up to 10 or 11 dimensions, which we can't directly perceive. This theory could help bridge the gap between general relativity, which explains gravity on large scales, and quantum mechanics, which governs the tiny, subatomic world. By combining these two, scientists hope to develop a theory of everything, a unified framework that explains all physical forces and particles in the universe. If superstring theory is correct, it could radically transform how we view black holes. For instance, it might explain what happens inside a singularity, or what truly occurs at the event horizon. Some versions of string theory even suggest that information swallowed by a black hole isn't lost forever, as previously thought, but is somehow preserved on its surface in a scrambled, quantum state. This idea ties into the famous black hole information paradox, which questions whether information that falls into a black hole is destroyed forever or can somehow be recovered. Stephen Hawking once argued that information was lost, which would violate the rules of quantum mechanics. But more recent theories, including those involving holography and string theory, suggest otherwise, that black holes might store information like a cosmic hard drive. Another concept related to this is the holographic principle. It proposes that all the information inside a black hole, or even the entire universe, might be encoded on a 2-dimensional surface, just like a hologram. This would mean our 3-dimensional reality is actually a projection from this encoded surface, a mind-blowing idea that challenges our very understanding of space and time. Michio Kaku and other researchers are using supercomputers to model how strings might behave near black holes, simulating conditions that could help them test these theories. While we can't yet directly observe what's happening inside a black hole, simulations give us clues and help refine our understanding. Eventually, these models could lead to technological breakthroughs or even change how we think about space travel, time, and the origin of the universe. We're living in a golden era of space science, with tools like the James Webb Space Telescope, gravitational wave detectors, and deep space observatories pushing the boundaries of what we know. Every discovery brings us one step closer to answering some of humanity's oldest questions. Where did we come from? What is the universe made of? And is there something beyond what we can see? Black holes, once considered purely theoretical, now sit at the center of these explorations. As we continue to unlock their secrets, we may also uncover new truths about ourselves and our place in the cosmos. Tiny strings with a pulsing sound constitute the fabric of the universe and describe not only gravity but also what it is. This occurs in the vicinity of wormholes and black holes. However, superstring theory also requires additional spatial dimensions that are so minute we are unable to see them using our current technology. Despite the difficulties, attempting to comprehend black holes, wormholes, and spacetime keeps scientists hooked, and it could lead to discoveries that alter our perception of the universe. Continuing in the same direction as before, the search for the theory of superstrings and other theories that seek to bring together the forces of nature is a tough challenge, but it might provide us with some insights into the way reality works. These hypotheses assert that there is more to the universe than the three dimensions of time and space we are aware of. Additional dimensions may exist, but because they are so small, we can't see them with our current technology. These dimensions may hold the key to comprehending phenomena like black holes, wormholes, and other mysteries of space. The superstring theory provides us with a fascinating illustration of the universe, declaring that matter and forces are just different manifestations of tiny vibrating strings. The rate of vibration of the strings varies, and each vibration produces a distinct particle, much like how a guitar string can make different sounds depending on how it vibrates. The basic particles of nature might be different vibrations of superstrings. If this were true, it would not only give us one explanation for the fundamental natural forces, like gravity, the strong nuclear force, electromagnetism, and the weak nuclear force, but also provide us with a fresh understanding of how the universe is constructed. It could answer some of the biggest questions in physics, like what dark energy and dark matter are composed of, things which make up most of the universe's mass and energy, yet we know very little about them. One problem is that string theory has not yet been demonstrated. The extra dimensions it describes are so insignificant that we cannot observe them directly. To see these dimensions would require extremely sensitive instruments, and even then, the evidence might be hard to detect. This complicates superstring theory's ability to be tested using standard scientific methods. Still, the theory is beautiful and logical, which makes it one of the most simultaneously intriguing physics concepts. Scientists are looking for new approaches to understand black holes. For example, quantum gravity is a field that tries to combine quantum mechanics and general relativity to explain how the universe functions. General relativity explains how large objects like planets and stars behave, while quantum mechanics focuses on the microscopic scale. The goal is that by combining these two theories, we can understand how gravity works on a small scale and uncover more about black holes and other features of space. The meeting point of quantum mechanics and general relativity is especially important when studying black holes, particularly near the event horizon, where gravity is extremely strong. We need a theory that can explain both quantum and relativistic effects. In fact, the singularity inside a black hole is one of the strangest places in the universe, a point where space and time become so warped that the usual laws of physics cease to function. To understand what's happening there, we require a theory that can unify general relativity and quantum mechanics. That's why people are developing concepts like loop quantum gravity and other quantum gravity models, attempting to correct these issues and provide us with a clearer picture of black holes. As we continue to explore black holes, one thing is certain: the more we understand, the more we realize how much there is still to learn. Black holes aren't just points of destruction, they're also regions of complexity and possibly even entry points to other dimensions, or the key to comprehending the very structure of space and time. Studying black holes is extremely significant. As our methods and theories improve, so too will our understanding of these enigmatic objects. Looking ahead, the next big leap will be in how we observe and investigate black holes. One of the most innovative developments in recent times is the detection of gravitational waves, ripples in spacetime caused by massive objects in motion, such as merging black holes. By discovering and studying these waves, scientists can learn more about the cosmos and black holes in ways previously impossible. Gravitational wave detection has already provided major insights into how black holes merge, and future experiments will likely reveal even more. Another exciting area of progress involves advanced telescopes and imaging methods. The Event Horizon Telescope, EHT, which took the first ever picture of a black hole in the M87 galaxy, demonstrates how technology can, in a sense, illuminate black holes. By combining data from radio telescopes around the world, the EHT was able to capture an image of the black hole's shadow, offering humanity a glimpse of one of the most mysterious objects in the universe. This image of the black hole's shadow marked a milestone in both astronomy and physics. It wasn't just a picture, it was confirmation of predictions made by Einstein's theory of general relativity over a century ago. The success of the Event Horizon Telescope, EHT, collaboration showed what could be achieved through global scientific cooperation, precision engineering, and theoretical insight. As technology evolves, scientists aim to capture even clearer, more detailed images. Future versions of the EHT or similar arrays might provide real-time video of a black hole's surroundings, revealing how matter behaves just before it crosses the event horizon. These advancements would offer profound insights into the nature of gravity, light, and time itself. Another critical avenue of research is the study of Hawking radiation, a theoretical prediction made by physicist Stephen Hawking. According to his calculations, black holes should emit a faint radiation due to quantum effects near the event horizon, eventually leading to their evaporation over astronomical timescales. Although we have not yet observed Hawking radiation directly, its implications are vast. It bridges quantum mechanics, thermodynamics, and general relativity, hinting at a unified framework that governs the cosmos. The quest to understand black holes, superstrings, and quantum gravity isn't just academic. It challenges the boundaries of human knowledge and may have future practical applications we cannot yet imagine, just as quantum mechanics once led to the invention of semiconductors, lasers, and MRI machines. In addition, the philosophical implications are enormous. If black holes can connect to other dimensions, as some theories suggest, or if spacetime itself is emergent from a deeper quantum reality, then our very notions of time, space, and existence must be reconsidered. The journey ahead is complex and filled with uncertainties. But that's what makes it exciting. We are at the frontier of understanding the universe, not just as passive observers, but as conscious beings striving to decode the cosmos. Each black hole we study, each ripple in spacetime we detect, each theoretical puzzle we try to solve, brings us closer to a more complete picture of reality. As new instruments come online, like the James Webb Space Telescope, next-generation gravitational wave detectors, and improved particle accelerators, we may find the missing pieces to theories like superstrings or loop quantum gravity. Or, we may discover entirely new principles that redefine the rules of the universe. In any case, the universe continues to challenge us with its mysteries. And in rising to meet those challenges, we deepen not only our scientific understanding but our sense of wonder and place in the vast, intricate tapestry of existence.